Says you're given the midpoints of the sides of a triangle. Find the coordinates of the vertices of the triangle. Very cool. I give such good questions for homework. I don't know. I don't always know what I'm doing. Okay, so do you understand? First of all, do you understand what it's giving you for information?
Yes.
It's giving you the midpoints of the sides. So we could graph this and get an idea of what it looks like, right? So we have negative. So let's make it a standard. You can estimate. It doesn't have to be super exact, but -3, 7. So let's say -3, and that's 7 up here. So we have point L right there. And then we have M is -5, 1. There's M. And then N, let's make that -8, 8. So that's -8, 8. And there's N. So those are the midpoints of the triangle, the midpoints of the triangle. Did you try to sketch it at this point? Yes, how did you go about sketching it? What'd you do, Lynch?
I made a rectangle.
Could you just try sketching it? Yeah, so I'd imagine you could sketch it, but what is it asking you for?
The vertices.
It's asking you for the other vertices, so is sketching good enough? No. Okay, so again, what's N?
N is
-8, 8, right? And what's L?
-3.
-3, 7, and M is 5, 1. Okay, so we understand there's a point. Let's just draw where we think we know the points are. We know there's a point somewhere out here, a vertice is somewhere out here, and a vertice somewhere up here. Do you agree with that? Yeah. Do we know what this first vertice is right here? No, let's just call it the coordinates AB. Let's call this one CD, and let's call this one EF. Is that okay? Do we have any idea what those numbers are? No, so let's just give them values. Okay, midpoints. These are midpoints, right? So let's call this the top corner A, this one B, and this one C. What's the midpoint of A and B?
AB.
Sorry, what's the midpoint of AB? L. What's the midpoint of CB? M. And what's the midpoint of AC? N. Exactly, N. So this coordinate right here, see the -3 right there? -3 has to be the average of what and what?
B and A.
Yeah, so A plus E over 2 has to be what? And B plus F over 2 has to be what? 7. And, I don't know, C plus A over 2, what does that have to be? -5. And D plus B, watch out for the cord, Luke. D plus B is going to be what? 1. And C plus E over 2 is going to be -8. And D plus F over 2 is going to be 8. How many different variables do we have?
6.
How many different equations do we have? 6. So theoretically, do we have enough information to solve?
Yes.
Absolutely. Okay, try that right now.
Cool.
Try that. See if you can solve. So what do you have to do a whole lot of if you're doing this?
Substitute.
Substitution. There's a lot of substitution. So first part of your homework, finish this. Finish that. Is there a place where you could plug that maybe to be helpful?
C plus E over 2 equals -8.
Yeah, there's a lot of different ways here. There's a lot of different things here. So you're matching A and E, and A matches to C as well, right? But also E matches to C. So you have to think about this here. So for example, what's linked? E is linked to A, and those are linked to C, right? F is linked to what? B, and those two are linked to D. So there you go. So basically we have 3B, sorry, and that's to D. 2 triangles, substitute, you can solve. Be careful. Yeah, a square, absolutely. If you draw this square, this is how you would notate a square, but the key thing that makes it a parallelogram is that, let's call that point A, point B, point C, and point D. Side AB is parallel to what? CD. and AC is parallel to BD. Exactly, not BC, BD. It's the pairs of parallel sides that make a parallelogram. Now, how do you notate that? You've seen this a little bit already. Matching arrowheads. Matching arrowheads means those two sides are parallel. So it's similar to the congruency. If you want to do another pair, you would do double arrowheads. Those mean those are parallel. We've seen that before. It shouldn't be anything too new for you. Now, what about opposite sides? Opposite sides are what in a parallelogram? They're what? They are congruent. That's correct. What about opposite angles? What? Take a guess. Yeah. Let's take a look at our parallelogram here. You know, let's draw another one. Looks like those sides are all, the opposite sides are congruent. What about the angles? Sure looks like it. So I'm just going to tell you that they are. What about consecutive angles? These two angles. So what is that called? What?
Complementary. Supplementary.
Is that right? Except I can't spell, right? And here's a question for you. What's a diagonal?
Two non-consecutive points that are attached by a line.
The diagonal is the line that connects the two, but you're absolutely right. So if we draw the diagonals, what happens to the diagonals? What do they do to each other? And that's a really poor line. They intersect. I agree that they intersect. What can you say about their intersection? They are oh, that's actually pretty cool. They are perpendicular. Yeah, they are perpendicular, but that's not what I was getting at, actually. They split what? They split what? They what? They bisect what? Each other. Yes, and they bisect the angle. So diagonals do what to each other? They bisect, and this is only in a parallelogram. Bisect each other. Bisect the angle and are what? You said it, Missy. Perpendicular to each other.
They are perpendicular.
There's only two in any parallelogram.
I know.
So yes, in every parallelogram, the opposite sides are congruent. The opposite angles are congruent. The consecutive angles are... Read it from the board.
I'm trying to...
Consecutive angles are... Good. And diagonals do what to each other? They bisect each other. They also bisect the angle. And they are always what? Perpendicular to each other. That's correct. Well, why are they? Do you want? We can actually try to prove that. Sure. So which one do you want to? If that's true, what do you know? You know that angle CAD is congruent to what angle? By what? That's by side, 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 right? Angle CAD is going to be congruent to what? CAB. Right? Are we okay with that? So we know that this angle has to be congruent to that angle. So it bisects that one, right? Ah, I see what you're saying. Ah, I see. We did write something that's wrong. You're absolutely right. Good job. And we also know that angle ACD is congruent to what angle? ACB. So this angle is congruent to that angle. So we just proved that they bisect each other. You're absolutely right. Now, you just brought up, I drew a regular parallelogram. Yeah, you're absolutely right. If it's not a regular, see this one.
More to the right,
exactly.
More to the left, they wouldn't be
you're totally right. Totally right. Good catch. If you draw this in, are they necessarily perpendicular? No, they are not. So they are only if they're perpendicular to each other. If what? If the parallelogram is what?
Regular. That's what I was.
You're absolutely right. Good job. Good catch. They're perpendicular. Yeah, if it's regular, then they'd have to be perpendicular. Yes, absolutely. Okay. Yes, because they would bisect each other, and then all those triangles would be side, side, side congruent. Yeah, right. Cool. In this case, this is congruent to this, and this is congruent to that side right there. We good?
Yep.
Very nice. Okay, let's move on. A collection of tiles that fill the plane with no gaps or overlaps. The tiles in a regular tessellation are congruent regular polygons. What's a regular polygon? Yes.
Regular polygon is a polygon where that is equiangular and equilateral.
Awesome. Awesome, awesome, awesome. How many people have made pretty pictures maybe in elementary school or in other classes with like blocks and stuff?
Oh, I thought you just meant
Pretty pictures, but with like blocks and stuff fitting together? Absolutely. That Tetris cube up there, that would be an example of maybe a 3D tessellation if you could put it all back together. Although no student of mine has ever been able to put it all back together. In fact, I'm the only one that's ever put it back together, and I had to cheat using a YouTube video. It's very, very hard. Even though there's something like 700,000 different ways to put it back together, it is very hard to put back together.
after school and try it.
But essentially, what's the key thing about tessellations? There's two things. You can't what?
Move them.
Can't overlap, and what else?
They have to be touching.
Can't be any gaps. Yeah, they have to be touching. Can't be any gaps. No gaps, and they can't overlap. Okay, sit down. Pair up. Work with somebody you have not worked with before. Page 3. Page 3. Page 3. Okay, a line of reflection. You should have an idea about this because we talked about them briefly, but the technical definition is a reflection in a line M is a transformation that maps every point P to another point P prime. And this didn't carry over, but it should be P with a little mark on top. So P with that little mark means you say P prime so that the following properties are true. If P is not on M, then M is perpendicular bisector of the line from P to P prime. And I'll draw this in a second. I'll draw this. And if the point is on the line of reflection, is it going to go anywhere?
No, because
It's reflecting onto itself. Exactly. So what I mean by that perpendicular bisector is this. If I have a point P and a line M, here is P prime. M is the line of reflection if, when I connect these two, and that's a really poor bisector right there, let's put it right here. M is the line of reflection if, when I connect these two, what angle does it have to form? 90. And if this point is A right here, not only does it have to be 90 degrees, what else has to be true? PA has to be equal to A P prime, PA, yeah, P prime A, that's right. So if that's true, line M would be called what? The line of? Reflection, exactly. The line of reflection. So if I said, for example, let's say I gave you this point M. That's a bad letter to use. Let's say I used R as that point, and I gave you this line right here. Let's call that line L. Where would this be the line of? Would that be R prime? No. It would be more accurately put where? Right about maybe here. Because this distance, it would need to be 90 degrees, and that distance would have to be equal to that distance. Does this make sense what a reflection means? So if you can reflect one point, what does that mean? If you can reflect a point, what can you also reflect? What? Yeah, anything you want. Because a shape is just a collection of points. So if you can reflect one point, okay, so if I gave you a triangle, A, B, C, and a line, let's call that line Q, could you theoretically draw the reflection of that entire shape? Would you have to reflect every one of these little points? No. How many points do you need to reflect?
3.
Yeah, A, you find A prime, B prime, and C prime, and then what do you do with those 3 points? You connect them, you make a triangle, exactly. So you don't need to reflect more than 3. You don't need to reflect more than 3. Using a compass, do you think you could do that?
Yes.
Yeah, maybe. You have to think about how to do that. Oh gosh, I get that right. I get it.
I think it sounds pretty simple.
You can tell. Hold on, keep it. You're going to work on it, right? But do you understand what a line of symmetry means? So a line of reflection is a line M that satisfies those two things. So if you're on the line, where does it reflect to? Yeah. So let's say that is point B. B is equal to B prime. Exactly. Symmetry. A figure has a line of symmetry if what? What do you think?
It can be folded onto itself.
That's right, I like that. If the figure can be folded onto itself. I like that. That's great. I really like that. That's very simple. So if I had a shape drawn on this piece of paper and I could fold it so it would fold onto itself, that would be a line of symmetry. How many lines of symmetry can a shape have? As many as you want. It could have an infinite number.
How?
Ah, you're going to have to think about that. But you need to be careful.